Hi, welcome back to Introductory Statistics. This is week 5. We're going to talk about linear regression. We'll cover chapters 7, 10, and 12 this week. So we're going to start by reviewing linear functions and the coordinate system. A linear function is a function whose graph is a line, and the linear function can be written in this form called the Slope-Intercept Form. F of x is equal to mx plus b, where b is the initial or the starting value of the function, and m is the rate of change or the slope of the function. And so y is equal to mx plus b. Again, m is the slope and b is the y-intercept. And the slope determines whether the function is increasing, decreasing, or constant. If the slope is positive, the function is increasing. If it's negative, if m is negative, it's decreasing. If m is 0, then the function is constant. So for example, if the slope is positive, it will be this case right here, where the function is increasing from left to right. And if the slope is negative, then the function is decreasing from left to right. And if the slope is 0, the function is constant, or stay the same. So here's some examples of linear functions. So for example, the orange line is the function that has positive slope. The slope is 1 over 3. And then this blue line right here has slope at negative 3, which is that means that from left to right the function is decreasing. And then finally this last line, y is 2x plus 1, the slope is positive 2, so it is also increasing. So notice that the slope, this function has slope 2, which is bigger than this function, which has slope 1 over 3. So that means that this function is increasing faster, is steeper than the other function. To calculate the slope of a function, we follow this formula, which is that we calculate the change in the output, which is the rise, divided by the change in the input, which is the run of the function. So it's a change in y divided by change in x. So y2 minus y1, x2 minus x1, it will be given 2 points on the function. So for example, if I have x1, y1, x2, y2, calculating the rise, which is the change in the y value, divided by the run, the change in the x value, that ratio is the slope. So for example, if you have a linear function that passes to these 2 points, 3, negative 2, 8, 1, then we can find the slope by calculating the change in y. Change in y is 1 minus negative 2, divided by change in x is 8 minus 3. So this is the change in y, this is change in x, and this function has slope 3 over 5, which is positive. That means the slope is increasing, the function is increasing. Note that the order of the x1, y1, x2, y2 doesn't matter. For example, if I were to switch the 2 and put, instead of subtracting 1 minus negative 2, I switch it and I put negative 2 minus 1, and then I similarly switch the x value. So instead of 8 minus 3, 3 minus 8, I get the same slope. So it doesn't matter whether I call this first point x1, y1, or I call it x2, y2, it doesn't matter. The slope will be the same. Okay, in fact, this last example is actually very important to what we're going to do this week, which is that if I know the slope and I know that it passes through a certain point, I can find the equation in slope-intercept form. So the slope-intercept form is the equation y is equal to mx plus b. I need to find what m is, what b is, to find my function. And so in this case, the slope is negative 3, so m is negative 3. So I plug negative 3 into the function. Now to find b, I can plug in the point 4, 8. Plug in 8 for y, 4 for x. I can find b. In this case, solve for b, I get b is 20. So my function is y is equal to negative 3x plus 20. This is the function that has slope negative 3 and passes to the point 4, 8. So that's a very important example that we'll need to know how to compute very soon. Okay, so the regression method describes how one variable depends on another. For example, if we look at height and weight. So let's look at this data set where we have 471 men aged 18 to 24, and the average height of these men was about 70 inches, and their overall average weight was about 180 pounds. And so, of course, naturally the taller men weigh more, and so the question is how much of an increase in weight is associated with a unit increase in height. So again, here's the data. The average height is 70 inches. Say the SD is 3 inches, the spread of the height. And then if the average, they say the average height is 180, and the spread of the weight is 45 pounds. And then suppose that the correlation coefficient is 0.40. So knowing all this, can we use the one variable to predict the other one? So here's the scatter diagram of the height and weight of these 471 men. And so every point on this graph represent the weight. Again, if I look at the point here, the x coordinate of that point is the height of that person, and the y coordinate is the weight of that person. So so this will have 471 dots. Each one of them represent one of the person in the study. So the regression line is this line right here. Is the, again, we haven't talked about how to find the line yet, but the regression line for y on x is the line that estimates the average value for y corresponding to each value of x. So given, for example, given an x value, which is the height, this regression line predict the y value, which is the weight for that particular height. And the SD line is this is the dashed line here. This is basically the line that take into account this data, the average height, weight, and then the spread of each of the variable, and so that's the SD line. And again, we'll talk about more about these lines specifically in a moment. So both the SD line and the regression line passes through the point of averages. So notice that there's a common point here that both of them goes to. This point right here is called the point of averages. It represents the average height and the average weight of these men. And so suppose that we call this point the point of averages x prime, y prime, where x prime is the average of all the x value and y prime is the average of all the y values. In this case, x is the height in inches and y is the weight in pounds. So the point of averages is 70, 180, because the average height is 70 and the average weight is 180. The SD line, the dashed line that we see here, has the following slope. The slope is the SDY divided by the SDX. It's basically the spread in the y direction divided by the spread in the x direction. The regression line, again, this is another line that also goes to the same point, 70, 180, but this has a different slope. It has it takes the slope of the SD line multiplied by the correlation coefficient. In other words, is R times SDY divided by SDX, where R is the correlation coefficient between x and y. In this example, R is 0.40. And so associated with each increase of 1 SD in x, there's an increase of only RSD in y on average. So that's what the regression line says. So the regression method, here's the regression line. It says that if I move horizontally with the amount of the spread in the x direction, so if I move horizontally by SD in the x direction, then I only move up. So if my run is SDX, then my rise is only R times SDY. And so this is the regression line, and it goes to the point of averages. And the way we think about the regression line is the smooth version of the graph of averages. And so, for example, if I were to plot, so for example, if I were to plot all these points where it shows the average weight at each height for each of the men. So, for example, if I pick a point here, so given this height, I look at all the people who has this height and look at all their weight and find the average of all their weight. So it will correspond to this point, for example. If I were to do that with all of these height, then the regression line is essentially the line that follows these averages. It's just the smooth version of of all these point of averages. Okay, so here's the example that we saw previously, which is when we pair up heights of father and heights of son. So each of the points here, you remember, is correspond to the height of a son and height of the father. And the average height of the father is 68 inches with the SD of 2.7. The average height of the son is 69 inches with an SD of 2.7. And then the correlation coefficient is 0.5. And so with so I want to talk more about the regression effect. And so the SD line is again the dashed line here, and the regression line is a solid line. And the dot shows that the average height of the sons for each value of the father's height. In other words, for every value of the father's height, say 66, the dot corresponds to the average height of all of the sons who has a dad with that height. And notice in this case that the regression line rises less steeply than the SD line, and this is called the regression effect. The regression line follows the dots, and the way you see that is that if you go back to this one, notice that the regression line, the SD line has a slope SDY divided by SDX, but the regression line, the rise is kind of hampered a little bit or dampened a little bit by the correlation coefficient. So it doesn't grow. The rise is not the full SDY, but only a fraction of SDY. So because of that, the slope of the regression line is rise less steeply than the SD line. And so let's kind of see if we understand what that means in an example. So suppose so looking at a preschool program that tried to boost children's IQs. Children are tested when they enter the program, which this is called the pre-test, and then they're tested again when they leave the program, also known as the post-test. And so on both occasions, the score average is about 100 and the SD is about 15. So it seems like the program have no effect. But if you look closely at the data, then something surprising shows up, and that the children who were below average on the pre-test had an average gain of about 5 IQ points at the post-test. And conversely, the children who were above the average on the pre-test had an average loss of about 5 points. And so looking at that, then what does this say about the program? Does that mean that this program kind of equalize intelligence? In other words, does the brighter kids who come into the program become duller as they play with the other kids, and that IQ kind of go down? And vice versa. This is desirable or undesirable, and so all these just speculation. And really, it turns out that there's nothing good or bad going on in this example, and the reason is because the children cannot be expected to score exactly the same on the two tests. There will be differences between the two score, and so And so when we make this scatter diagram for the test scores, the test scores spread around the SD line into that familiar football shape that we saw in the previous lecture. And so the spread around the line makes the bottom group come up and the top group come down, and that's really nothing else of it. So let's kind of see maybe the best way to kind of see a graph of this. So in a moment I will show you that graph. But so virtually in all the retest consideration, the bottom group on the first test will, on average, show some improvement on the second test, and whereas the top group on the first test will, on average, fall back. So this is the regression effect, and it has to do with what I mentioned earlier, that the slope is sort of dampened a little bit by the correlation coefficient. And so thinking that the regression effect must be due to something important is called the regression fallacy, and is something we want to be careful with. And so here's what the regression effect says. The SD line represents students who did this about the same on the pretest. So again, here's the scatter diagram of all the score, where each dot represent a test score and also a retest score. So every dot represents a student with his test score and also his retest score on the x and y coordinates. And so let's look at the example of some students who did not do well on the first test, which means they did below the average. Here's the point of averages. So these students right here on the left side here, they're on the first test, which is on the x-axis. Notice that their score is below the average, which is right here about. And notice that they actually did better on the second test because if they were to do the same on the second test, they would have been on the SD line. And then students who did well on the first test, for example, these students here, because their score is above the average, notice that on average they did worse on the second test because now their score is below the SD line. So again, right, I think that the easiest one to understand is probably that these students here, because these students' scores is above the average on the first test. That means they did better on the first test. But notice that their score on the second test is actually kind of below the SD line, which means that so for example, look at the student right here. His score is a certain amount above the average on the x-axis, but it's not the same amount above the average on the retest. So which means that he did a little bit less worse than on the second test than he did on the first test. And then for these students here, they've done better on well, first of all, because their score is below the average, that means they did worse. They did below average on the first test. But notice that these points are above the SD line, so that means that relatively speaking, they did better on the retest. Again, if the point is on the SD line, that means they did the same on both the first and the second test. Because if I were to have a point on the SD line, what that means is that whatever amount they did better on the first test, they did the same amount better on the second test. So that means that they did about the same on both tests. So this is the regression effect. It says that the top group did a little bit slightly worse on the second test, whereas the bottom group did a little bit better on average on the second test. And so I think maybe another example that can clarify this is to look at the observed score, the observed test score versus the true score of the student. And so here's the basic equation. It says that the true score of the student plus the chance error. Maybe you can't expect the student to do the same on both tests, so there's some kind of an error there. And so their true score plus the chance error gives you the observed test score. And so again, assuming that the IQ score follows this normal distribution, which is reasonable. So here's how we can kind of think about this. Suppose we have a student who scored 140 on the first test, which is their observed score. There are two explanations for this observed score. One explanation is that their true score is below 140, which means that they have a positive chance error, meaning that the true score is below 140, the error was positive, which makes their observed score, so the true score is below 140, and the chance error is a positive error, which makes their observed score higher than the true score. So that's one explanation. Another explanation is that the true score is above 140, and so again, 140 is the observed score here. So there's two explanations. One explanation is that their true score is actually 135, which means that the error is the chance error is positive, which and then another explanation is that their true score is say 145, which means it's above the observed test score. And so based on those two possibilities, the first explanation is actually more likely, and that's because if you look at this distribution, there are more people, right? If this student is above average, then it's more likely that his true score is to the left of it, because there's more people who belong to who has score that is on this end of the spectrum rather than on the right side. And so because of that, this is another way to think about the regression to the mean, which is that if this person scored better on the first test, then it's likely that on the second test they'll do a little bit worse because they're regressing towards the mean. They're regressing towards their true ability. So if the true ability is 135 and they happen to be lucky and did better than 135, then likely on the second test they'll regress towards their true ability by doing a little bit worse than on the first test. So that's another way to think about that regression effect. And so, so this slide basically explains that this model accounts for the regression effect. If someone scores above the average on the first test, the true score is probably a bit lower than the observed score. That means that if the person takes the test again, we predict that the second score would be a bit lower than the first score. And then on the other hand, if a person scored up below average on the first test, we estimate that the true score is probably a bit higher than the observed score. That means that our prediction for the second score will be a bit higher than the first score. So the regression line is again given by this equation: y is mx plus b, where the slope is the correlation coefficient r times sdy, the sd of the y values divided by the sd of the x values. And the y-intercept can be found by plugging in the point of averages. If I know the point of averages, I can find the y-intercept. So this is the slope, and the y-intercept can be computed by plugging in the point of averages. And so let's do an example. Suppose that we look at the education and income of a group of women at the age of 25, between the age of 25 to 29, and the average income education is 13.0 years, and the SD is about 3.4 years. Say the average income is about 18,000, and the SD is 20,000 with the correlation coefficient of 0.37. And so now we're going to find the regression equation for predicting income from education, which means that if I'm given education, can I predict income from education? And then we're going to use that equation to predict the income of someone whose educational level is 8 years, 12 years, and 16 years. Okay, so here's how we do that. So based on the regression equation, the slope of this line must be r times sdy divided by sd of the x values. And so the r is 0.37. The spread of the y values is $20,000, so it's 20,000 on top, and the spread of the x value is 3.4, and that's given by the problem. Again, because we're predicting income from education, x is the education and y is the income, and so that's why the sdy refers to the sd of the income, which is the 20,000, and then the sd of x refers to the spread of the education, which is 3.4. So if I do that out, I get that the slope is about $2,176 per year. Again, I'm dividing a dollar by year, so this is the unit of the slope. And so now, so that means that for every year of education, my gain is about $2,000 per year of education. So now that I have the slope, which is 2,176. I need to find b. To find b, we plug in the point of averages, and in this case the point of average is 13, 18,000. That's because of this. The average is 13 years of education, 18,000 of income. So plug in the point of averages, we can find that b is this number. So here's my function with the slope and the y-intercept, and now I can use it to make prediction. So in part b, if I plug in 8, that means that if I have 8 years of income, 8 years of education, then my income is about 7,000. If my education is 12 years, my income is about 15 or 16,000. And then finally, if my plugging in 16 into the equation give you the income of someone whose education is about 16 years of education. And so that's an example of how we can use the regression line to make some prediction about someone's income based on their education. Here's another example. We saw earlier that looking at a group of men whose average height is 70 and whose SD is 3 inches, and their average weight is 180, and the SD is 45 pounds, with the correlation coefficient of 0.40, we're going to use the regression line to predict weight from the height. and so that means the height is x and the weight is y. And again, here's the slope equation. R is 0.4. The spread of the y values, which is the weight, is 45. The spread of the x value, which is the height, is 3. So my slope is 6. And to find b, I plug in the point of averages, which is 70, 180. 70 is for the height, the average height. 180 is the average weight. My b is negative 240 if I solve for b. And then my function is y is 6x minus 240. Now to make prediction, if I want to predict the weight of someone whose height is 73 inches, I plug in 73 and I get that his weight is predicted to be about 198 pounds. Okay, here's another example. This example is a little bit of a different example. Suppose that you have some data that explains the relationship between the math SAT scores of a group of first-year students and the corresponding GPA ranging from 0 to 4. And by looking at that data, the data says that the average SAT score of these students is about 550 with SD of 80, and then the average first-year GPA is about 2.6 with the spread of about 0.6. And suppose that the correlation coefficient is 0.4. So how can we use this data to make some prediction about GPA and SAT score? Well, suppose that the percentile rank of a student on the SAT is 90%. That means that they did better than 90% of the students among the first-year students. We want to use that data to make prediction about the percentile rank of the GPA. So if we know something about SAT score, can we predict something about how they perform on the first year in terms of the GPA? And so one way to do this is to find the regression line as we did in the previous problem, and then plug it in as we did previously. But it's actually a much easier and faster way of doing this problem, which is that we can look in the z table for 0.90. Again, 0.90 is the percentile. So look inside the z table for 0.90 and find the corresponding z score for 0.90. And again, the z score comes from the row in the column of the z table. So you look at 0.90 inside the z table. The z value will be 1.28, and so that means that this student's SAT score is 1.28 SD higher than the average. Again, that means that if their SAT score is 90% better than the other students, that means that their score is 1.28 SD higher than the average. Now, by the regression method, this student's GPA is not one full SD higher, but it's only R times the SD higher. So that means that if I take R and multiply by the 1.28, I get so 0.4 times 1.28 is 0.51 SD. So that means that again, if you're on the SD line, the fact that this student score 1.28 SD higher on average on the SAT score, if you're on the SD line, we would have concluded that their performance on the GPA would also be about 1.28 SD higher. But the regression effect says that their GPA performance is only 1.28 SD times the correlation coefficient higher, which means that in this case their GPA performance is only 0.51 SD higher than the average. So again, this is the regression effect. Even though they did much better than on the SAT, which is 1.28 SD higher, their performance on the GPA is only 0.51 SD higher than the average. And so now we look in the z table for z is 0.51 and find that the area below 0.51 is 0.695, which means that this student has a percentile of about 70% on the GPA. So what that says is that even though their SAT score is 90% higher than the students in the first year students, because of the regression line, we predict that the performance on the GPA is only 70%. So this is if you should try to do this problem with the regression line, and you find out that this is a much easier way of doing this problem. So there'll be actually a couple of web work questions that will ask you to do it this way. And so once you start your web work, in some of the hints, it will refer to this example of how to do the problem. So watch out for this similar problem on web work for this week. Okay, so I want to kind of finally explain some intuition behind this regression line, or also known as the least squares line. And so sometimes the points on the scatter diagram seem to follow a line, and so the problem that we discussed in this section is how to find the line that best fits these points. So there's a little bit of a compromise here, because if I were to move the line closer to some points, again, I'm trying to find a line that best fit the data, and if I were to move the line closer to some points, that will increase my the distance from other points. And so we want to kind of find a compromise to find the line of best fit. And so the way it works, that we're going to take 2 steps. The first step is to kind of define the average distance between a line and all of the points. And the second step is to kind of move the line until this average distance is as small as possible. I think the kind of best way to think about this is to kind of see an example here. So let me kind of show you an example here. So suppose I have my scatter diagram, and I draw a line, just any line for now. I can measure the distance between all the points to the line. So for example, right, this vertical distance, for example, if this point is further away from this line based on this vertical distance, so these are the errors, because the line is an attempt to describe the data, and because the data is off the line, these vertical distance between the point and the line is the error. Because if I were to use the line as a prediction, I would make the prediction based on the line, and this vertical distance would be the error from my prediction, between my prediction and the actual value of the point. And so the line of best fit is the line that would minimize this total errors. If I were to add up all these errors, the line of best fit is the line that has whose sum of all the errors would be the least. So among all possible lines, it turns out that the regression line, or the least squares line, is the line that makes the smallest RMS error in predicting y from x. So remember from one of the previous lectures, we talked about RMS as the root mean square. So if we were to look at all the errors and find the root mean square, then it turns out that the regression line that we talked about in this section is the line that minimized the RMS error. And that's basically what this line is, what this slide is about here. And so let's see. Okay, and then another point I want to make is that there's actually 2 regression lines across any scatter diagram. So here's the picture. Depends on what we're trying to predict. We might have we have 2 options for regression line. So for example, on the left-hand panel here shows the regression of weight based on height. That means that given a height, we want to predict weight. Whereas the other regression line says that is the regression line that says that given a weight, we want to predict the height. So again, this line is the line we use if we were to be given the height and we want to predict the weight from it. We will use the other regression line if we know the weight and we want to predict the height. So maybe let's see an example of this dashed line is the SD line. So let's kind of see an example to kind of explain this further. So for example, here's the suppose we have some data that correspond to the IQs of men and women, and suppose that the IQ scores are scaled to have an average of 100 and the SD of about 15, both for men and women. And suppose that the correlation between the IQs of husbands and their wives is about 0.50. And so a large study of families found that the men whose IQ was 140 had wives whose IQ averaged 120. And so suppose that we look at the wives in the study whose IQ is 120. The question is, should the average IQ of the husbands be greater than 120 And so let's kind of try to understand this problem. Okay, so let's look at the first picture on the left here. This says that if I were to look at all of the wives whose husband has an IQ of 140, then it will fall within this vertical strip. So again, right, if you were to look at all the dots, there'll be a bunch of dots, and look at all the dots that are in this vertical strip. In other words, all the wives whose husband IQ is about 140. If I find the average of all of the IQ of all these wives along this vertical strip, I get this X point, and that's where the 120 comes from. That means that the IQ of all the wives of men whose IQ is 120 averaged out to be 120. Sorry, let me say that again. This says that looking at all the wives whose husband has an IQ of 140, the average IQ of those wives is 120. Now, suppose I were to look at the other direction. In other words, we look at the question says that if I were to look at all the wives whose IQ is 120, so horizontally now I'm looking at all the I guess if I were to look at the average IQ of the wife, and if the average IQ of the wife is 120, I want to know whether the average IQ of the husband is greater than 120. And so so now we're looking horizontally now, right? And so we're looking at all of the husbands whose wives' IQ is 120. And now, because of again, we said before that we have two regression line. This regression line is that if I know the husband's IQ, I can use this regression line to predict the wife's IQ. The other regression line is the regression line I will use if I know the wife's IQ, and I want to use that to predict the husband's IQ. And so it depends on the problem. We have two possible regression lines, and for this problem, so let me go over here and explain this. And so for this problem, the conclusion is that the average IQ of the husbands is actually going to be less than 120, and in fact it turns out to be around 110. And the reason is because, again, this is confusing because if I were to use the first regression line, the regression line of if I know the husband's IQ to predict the wife's IQ, then that regression line says that regression line corresponds to this vertical strip. It looks at all the wives whose husband has an IQ of 140, and find the average of that, and that gives you that point here on the regression line. But now that we switch it around and says that, well, what if we were to look at the wife's IQ to be 120 and consider the average IQ of all their husbands, then we're looking at now a different group of people, right? We're looking at all the people who lives in this horizontal strip, not the vertical strip. So now we're looking at a different regression line, which is this regression line on the right here, this dotted line here. And so because of that, notice that we're going to see that that IQ is going to be about 110, which is right about here. So the reason why we know that's because if I were to look horizontally on this this strip and find the corresponding point on this regression line. So again, if I were to look horizontally, it looks like it's about right here. This says that the average IQ of all the husband whose wife's IQ is 120 is approximately around right here. Again, I'm looking horizontally, so that if I match it up, then on this line, then I see that this is about 110 because the point of average is 100. So it looks like the average of IQ of all those husbands whose wife IQ is 120 average out to be about here, which is about 110. And so the thing that to be careful here is that depends on the question, where we might be looking at very different set of families here. On the first data, which says that on the first regression line, where we look at all of the wives whose husband has an IQ of 140, their average IQ is 120. But on the question that we're asking now, we're looking at a different set of people, because now we're considering all of the husbands whose wife IQ is 120. So now this is a different set of families. So that's why we have to be careful that we look at, depends on the problem, we might have to consider a different regression line. Okay, that's the end of this lecture. Thank you for watching.